with millisecond duration and extremely high brightening temperature. Up to present, few hundred of fast radio bursts have been detected, and a dozen of them show repeating behaviors. However, their physical origins are still not well understood due to the complexity and the diversity of the observation. The galaxy FRB 200428 was detected to be associated with the X-ray burst from galaxy Magnetized, implying that at least some fast radio bursts originated from Magnetized born from the core collapse of massive star. However, such a formation channel is challenged by the observation of another nearby FRB, 200120G, which was localized to be in a global cluster of the nearby galaxy M81. The extremely old age of the host global cluster implies that the FRB is more likely produced by an older object or a system associated with a compact binary merger. Multiple origins for the FRB population seem increased likely. The millisecond duration and excessive DM of FRB suggests that FRB should be from the compact object at the cosmological distance, and the extremely high brightening temperature implies that the radiation mechanism of FRB must be coherent. Because FRB are emitted at the radio band, propagating effects such as dispersion, dilatation, temperature scattering, scintillation, and depolarization play important roles to interpret observations and constrain the FRB environment. The multi-wavelength counterpart of the actual galaxy FRB are very hard to detect due to their low luminosity. So the information on propagating effect would provide important clue for physical origin of FRB, especially for repeating FRB source that can show dynamic evolution of the propagating effect. For a repeating FRB source, the variance of his DM and RM can be used to study the propensity of his near-source plasma. In magnetized plasma, the natural mode of electromagnetic wave are usually left and right circular mode. We can write the dispersion relation as the equation. The DM term leads to the time delay, and the difference of RM term between two models leads to the body rotation. The RM corresponds to higher order term in the wave dispersion relation. This is the reason why for certain evolving plasma, the RM variation is more sensitive than that of DM. On the other hand, different from DM that usually has a significant contribution from the intergalaxy medium. The observed RM, especially when it is large, is more likely contributed by the magnetized environment near the FRB source. So the measurement of RM variation is important to reveal the astrophysics environment of and the physical origin of FRB repeater. In observation, Faraday rotation is measured by the wavelength-dependent polarization angle. There are two main necessary conditions to measure the Faraday rotation. First, the electromagnetic wave must contain a significant linear polarization component, which can be used to measure the polarization angle rotation. Second, the polarization angle must be proportional to the square of wavelengths in a local region, which requires that the field strength must be less than a few hundred Gauss for GHz wave. For extragalaxy FRB, the observed RM include contributions of various components along the line of sight, including Earth's ionosphere, interstellar medium in Milky Way and host galaxy, intergalaxy medium, and local plasma. Because the first four contributions are usually small, observed RM larger than a few thousand radians per meter square would be expected to be mainly contributed by the local plasma near the FRB source. For a cold magnetoionic plasma, the Rm is proportional to the integral of product of electron density and parallel magnetic field. And the measurement average field depends on the field configuration along the line of sight. Although there is usually a large-scale field near a magnetized object, there are some fluctuations due to MHD turbulence. So both a large-scale ordered field and the turbulent field are involved in various astrophysical scenarios. If the magnetic field is ordered in large scale, the average field would be of order of the local field. However, if the magnetic field is totally turbulent, the observed average field would be suppressed differently. So the measured average field should depend on the field configuration. Taking a differentiation of the first equation, we can say that the relative Rm variation is the sum of the relative variation of Dm and the average field strength. For example, FRB 190520b appears Rm reverse during a few months. That means that the field configuration is dynamically evolving. Recently, some FRB repeaters were reported to appear complex, diverse variation of body rotation measures, which implies that they are surrounded by an inhomogeneous, dynamically evolving magnetized environment. For example, the first known repeater, FRB 121102, shows the largest Rm of 10 to 5 radians per meter square in all FRB, and decreased by 30% during 1 year. FRB 1A0916B with 16-day periodic activity shows Rm variation with a random component and a secular component. It is interesting that the long-term Rm evolution and the burst-to-burst Rm variation appear to be unrelated to the periodic activity during the 3 years observation. FRB 201124A shows irregular Rm variation over 1 month and become constant later. Such evolution trends has been observed in some pulsar binary system. FRB 190520b shows the second largest Rm value among all observed FRB sources and a significant Rm variation during a few months. The observed Rm reversal suggests that the Rm variation is mainly due to the change of the magnetic field configuration. So, in conclusion, Rm variation seems to be a common feature for many FRB repeaters, and some of them show both random fluctuation and systemic secular evolution. For random Rm variation, the most likely scenario is that there is a plasma screen with inhomogeneous medium near the FRB source, and the relative motion between the FRB source and the screen causes the irregular Rm variation. The Rm strong function is used to present the mean square Rm difference between two paths separated by a transfer distance, which depend on the power spectrum, the fluctuations of the electron density, and the magnetic field. If the Rm variation is due to the change of the relative position between the FRB source and the plasma screen, the position-dependent strong function could be directly written as the time-dependent strong function. For a given spectrum of electron density and magnetic field, the Rm strong function could be written as the bottom two equation, which depend on whether the power power spectrum of the fluctuation is steep or shallow. For the steep spectrum, the fluctuation are dominated by the large-scale turbulence, and for the shallow spectrum, the fluctuation are dominated by the small-scale turbulence. In particular, Kolmogorov scaling with the spectrum index of minus 11/3 has the spectrum index of 5/3. So the larger the separation, the larger the Rm variation. Based on the definition of strong function, the variation of Rm is the square root of the strong function. We can say that the relative Rm variation is small in a short term and reach a maximum value when the relative displacement larger than the turbulence outer scale. The measurement of Rm strong function of some FRB repeater reveals that the strong function is proportional to the time to 0.2 to 0.4. Leading to the power spectrum index of the fluctuation to be minus 2.2 to minus 2.4. So the Faraday screen of these FRB repeaters have the shadow spectrum, which means that the variation is dominated by the small-scale fluctuation. Because the magnetic field spectrum is usually steep, so the observed results suggest that the fluctuations are made by electron density with the shadow spectrum. In physics, the electron density with the shadow spectrum naturally arises in supersonic turbulence. On the other hand, some FRB repeaters show relative Rm variation during a few months to a few years. So the turbulence outer scale could be constrained by the typical observed time for Rm variation. For a relative velocity of a few hundred kilometers per second, the length scale should be less than 10 to minus 4 parasecond. A secular Rm evolution may be attributed to the expansion of a magnetized shell or the orbit motion of a binary system. In the former scenarios, the electron density and the magnetic field are usually related by an energy equation, magnetic freezing or shock compression. Due to the expansion, the electron density might decrease with the radiance and the shock might be decelerate. So the Rm variation satisfies a power law distribution during a long term. Another probability is that the secular Rm evolution is caused by the orbital motion of a binary system. And the companion could be a stellar object or a massive black hole. In these scenarios, because there is a large-scale magnetic field near the companion, the Rm variation might be periodic due to the orbital motion. However, the random Rm variation by MHD turbulence might smash out the clean periodic signal in the Rm variation. Next, we discuss some possible astrophysical processes that might cause the Rm variation of FRB repeater. We first consider that the Rm variation contributed by a supernova remnant. Radio polarization observation of young supernova remnant suggests that the magnetic field in SNR are largely disordered. If the magnetic geometry along the line of sight keeps unchanged, the Rm would be a pure long-term evolution due to the SNR expansion. However, such a scenario cannot explain the irregular Rm variation showed by some FRB repeater. When SNR propagates in highly inhomogeneous interstellar medium, it generates a pair shock upon interacting with a gas cloud. and induce turbulence in the magnetized medium. In these scenarios, the relative motion between the FRB source and the SNR will lead to the RM variation. If the size of the SNR local structure is larger than the gas cloud, the observed RM variation implies that the SNR is young with age less than a few hundred years, and the local and have a local anisotropic. If the size of the SNR large-scale structure is less than the gas cloud, the SNR is allowed to be relatively older. However, this is challenging to resolve such a small-scale density structure due to the limited resolution in observation. There is some evidence suggests that FRB source might be in a binary system. First, FRB 1A0916B show periodic activity, which might correspond to orbit period of a binary system. Second, the M81 FRB was found to be associated with a global cluster, which contains many closed binary systems. Third, there are some similar polarization propensity between the radial pulsar in binary system and the FRB repeater, including Faraday conversion and RM variation. If an FRB repeater is in a binary system, in order to explain the large RM value of an FRB, the mass loss rate of the companion should be enough large, so the companion could be a massive star or a giant star. When FRB repeater is in a binary system, both orbital motion and the dynamic evolution of the companion wing could cause the RM variation. If the magnetized companion have a large-scale magnetic field, the RM variation would be periodic. However, the turbulence in stellar wing may smash out the apparent RM periodic evolution. In addition to the dynamic evolution of the stellar wing, the turbulence in the stellar wing can also cause the RM variation in a short term. For the companion stellar wing with an anisotropic distribution angle of 1 radius, the relative RM variation reach maximum at a few weeks, which is consistent with the observation of some FRB repeaters. Stellar flares are triggered by magnetic energy released near the stellar face and are accompanied by corner mass injection. In general, the larger the released energy, the longer the flare duration. Different from the stellar wing scenarios, the contributions of DM and RM from the stellar flare mainly depend on the time difference between the stellar flare and the FRB. Because FRB emissions and the stellar flare in a binary system should be physically independent, the RM would be various during a very short term. Such an extremely RM variation has not been observed in any FRB repeater, which is inconsistent with the current observation. We also consider the RM contribution from the pair plasma from a neutron star, including pulsar wing nebula, including pulsar wing nebula, and magnetized flare. There are 3 reasons the RM contributed by the pulsar wing could be ignored. First, for pair plasma, due to the symmetry of positive and negative charge, only the net charge contributes to Faraday rotation.
Left.
Oh, okay, thank you. Second, RM is suppressed by the relativistic motion of hot electrons. Third, RM measurement requires that the electromagnetic wave frequency must be larger than the cyclotron frequency. Although a neutron star has a strong magnetic field near its surface, this region cannot contribute to the observed RM. A pulsar wave nebula is produced by the interaction between the pulsar wave and the supernova remnant. In this process, the kinetic energy of pulsar wave is transferred to the thermal energy. Or the Moore pair might be generated by the magnetic reconnection. The number of net charge keeps unchanged, which cannot contribute to the RM. For magnetar flare, because a part of energy is transferred to relativistic pair, the RM contribution is also expected to be very small for the same reason. The extremely large RM of radio cloud magnetar have been observed in the vanishing of a massive black hole. So it has been suggested that the large RM observed in some FRB repeater might be a result of the source is near a massive black hole. The larger the black hole mass, the larger the density of outflow from the accretion disk, leading to a larger RM. And the RM variation is accounted for by turbulence and dynamic evolution in the outflow. Because the outflow from a massive black hole might interact with the nearby gas cloud, the turbulence outer scale is the minimal value of the intrinsic homogeneity scale and the gas cloud size. For typical value, RM variation reach maximum at tens of years. In general, the time scale is too long to interpret the observed short-term RM variation, which requires that the FRB source must be very close to the black hole in order to have observed rapid RM variation. We should know that the mass of a massive black hole cannot be large in this scenario because many FRB repeaters was localized at the position far away from the center of their host galaxy. We make a brief conclusion for various scenarios as follows. For supernova remnant scenarios, a large relative RM variation within a few years requires that the supernova remnant is young, or the size of the dense cloud in the interstellar medium is very small. If the RM variation caused by the companion medium in a binary system, it is more likely from the stellar wave of a massive star or a giant star. Outflow from a massive black hole could provide a large RM and a significant RM variation if the FRB source is in the vanishing of a black hole. The RM variation contributed by stellar flare and contributed by the pair plasma could be ruled out because these scenarios are inconsistent with the current observation. In addition to the RM variation, some others observed features might originate from the near source plasma, such as the temperature scattering and depolarization. Although the temperature scattering has been found in observation of some earliest FRB, the physical origins is mysterious still long term. The top right picture shows the scattering time of FRB and radio pulsar. We can see that temperature scattering of some FRB are much longer than that of radio pulsar at a higher latitude. So the FRB temperature scattering must occur outside the Milky Way. On the other hand, for radio pulsar, the temperature scattering has a positive correlation with the observed DM. This is because both the scattering and the DM originate from the same region, that is interstellar medium. However, for faster radio bursts, with the DM mainly contributed by the intergalaxy medium, the lack of any correlation between the scattering time and the DM suggests that the intergalaxy medium cannot contribute to the observed scattering time. Okay, last slide. Recently, From 2020, found the evidence of frequency-dependent depolarization of some FRB repeater, which can be explained by RM scatter of a multipath propagation of a plasma screen. The large value of RM scatter implies that the plasma screen has a large electron density and a strong magnetic field, which seem to be located near the FRB source. Furthermore, FRB scatter are correlate positively with the temperature scattering for this FRB repeater. The larger the RM scatter, the larger the scattering time. This thus suggests that depolarization and the temperature scattering originate from the same region and have the physics connection. This is a brief summary of my report. Thank you for your patience.
Okay, thank you, Yuan Pei.
Thank you.
Are there any questions from the audience, on-site participants here? Okay, one question.
Hi, thanks for this really interesting talk. I was curious about, maybe this is a naive question, but I was curious about the supernova example you showed. So you mentioned that the turbulence outer scale, the large relative RM variation requires a certain scale for the supernova remnant, or it to have a very young age. I wonder if there's any constraint that could also be placed on the configuration of the clouds that it's interacting with. For example, the size or the density.
Based on the current observation, there are two possibilities. First, let me change to the slide. First, if the turbulence is mainly contributed by the local medium in the supernova remnant, this requires that the supernova remnant is young, with age less than a few hundred years. Another possibility is that the turbulence is mainly contributed by the gas cloud near the SNR, which requires that the size of the gas cloud is less than 10 to minus 3 parasecond. So, because the RM variation time scale is small, especially for 1905 20, which have a RM variation time scale of a few months. It's a very small variation time, leading to a small turbulence outer scale.
Thank you very much. Very interesting.
Thank you.
Okay, thank you, Yuan Pei. Maybe we can discuss later on the discussion session more. Thank you so much for informative talk. Okay.
Okay, thank you.
Thank you.